July 2025. Astronomers detect something extraordinary hurtling through space toward our solar system. They call it 3 Atlas, only the third interstellar object ever observed entering our cosmic neighborhood. At first, it seems like another wandering rock from the depths of space, but then the James Webb Space Telescope locks onto it and discovers something that changes everything. There's a glow emanating from its core, a steady pulsing light that no ordinary rock should be capable of producing. This isn't the faint reflection of sunlight or the random flickering of ice turning to vapor. This is something else entirely. The numbers don't lie. The object's brightness measures 3 times what any model predicted. There's no comet tail streaming behind it, no erratic flickering across its surface. Instead, its rotation is clockwork, steady, precise in a way that feels almost deliberate. Then the data gets stranger. Multiple research teams working independently confirm the same shocking discovery, a thermal heartbeat pulsing from the object's core every few hours, accompanied by a cascade of radio signals that match no known natural phenomenon in our catalogs. If these readings are accurate, if the instruments aren't lying to us, then we might be looking at the first evidence of something constructed rather than formed by nature, and it's heading our way right now. August 6, 2025. Deep in the endless stream of data flowing from the James Webb Space Telescope, a team of operators monitoring the NAR-SPEC instrument notices something that doesn't add up. The first infrared frames of 3I Atlas reveal a concentrated glow at the object's center. This isn't the scattered haze you'd expect from reflected sunlight or the diffuse cloud that typically surrounds active comets. It's a tight, isolated source of light, bright enough to completely outshine any surrounding dust or debris. The readings come through clean with no indication of instrument malfunction, no contamination from solar flares, nothing that would suggest an error in the data. When the team examines the raw plots, the heat signature stands out dramatically. There's a white, hot core that gradually fades into colored bands, all perfectly centered on a nucleus too small for any telescope to actually resolve into a clear image. Dr. Lena Marovich, the senior instrument scientist leading the Webb team, immediately checks the calibration logs and orders the analysis run again. The results don't change. The emission remains steady, holding at levels 3 times higher than any predictive model suggested was possible for an object of this estimated size and distance. There's no tail, no flickering, just a fixed and unwavering beacon shining in the darkness of space. The team's internal communications explode with questions. Is this outgassing, the normal release of frozen gases heated by the sun? Or are they witnessing something completely unprecedented? They immediately dive into the archives, pulling up earlier observations from Hubble and the TS satellite from the summer months. Those older records hint at something already unusual. The object was already glowing with unusual intensity far beyond Jupiter's orbit, long before solar radiation should have been strong enough to trigger normal cometary activity. But even those earlier observations don't match the clarity or sheer intensity of what Webb is now seeing. To the operators studying these readings, one thing becomes crystal clear. This heat isn't coming from the surface being warmed by the sun. It's emanating from deep inside the object itself, and whatever is generating it doesn't follow any of the usual rules. The optical survey teams, led by the ATLAS group operating in Chile alongside analysts working with Hubble data, begin their own intensive investigation. Their primary concern centers on the object's brightness. By every standard metric used in astronomy, 3I Atlas shines at nearly 3 times the intensity expected for a celestial body of its estimated size at this distance from the sun. When they plot light curves over several weeks of observation, tracking how the object's brightness changes over time, they find something remarkable: a steady, unwavering output. No dips in brightness, no sudden surges, none of the flickering you'd normally expect from jets of gas erupting from an icy surface or from the uneven terrain of a tumbling rock. For comparison, typical comets brighten and fade as they tumble through space, their icy crusts venting volatile materials in irregular bursts and fits. Here, the brightness pattern is almost completely flat. The object rotates with a measured period of approximately 6 hours, which should be more than enough time to reveal any significant surface activity as different faces turn toward our telescopes. But nothing appears. No jets, no geysers, no bright spots that come and go with the rotation. Hubble's high-resolution imaging capabilities search for the classic cometary tail, that streaming plume of dust and gas that signals ice sublimating into vapor under solar heating. Instead, what they find is an object wrapped in a tight, teardrop-shaped cocoon, more like a shroud than the dramatic tail we'd expect. The analysts note something particularly puzzling even at 6 astronomical units from the Sun. Where solar radiation is weak and most comets remain completely dormant, 3I's Atlas is already blazingly active, glowing against the cosmic black. No model of solar heating, no standard theory of outgassing behavior can explain either the intensity or the timing of this activity. These contradictions leave the optical observation teams facing a genuine puzzle, a celestial body that's too bright, too steady, and too self-contained to fit into any familiar category. The usual rules that govern comets simply don't apply here. For researchers across multiple institutions, the logical next step becomes obvious. If the light isn't being generated by surface processes, then perhaps the answer lies deeper inside. The infrared analysts working with Webb begin carefully dissecting time series data, searching for any discernible pattern in the heat radiating from 3-eyed Atlas's core. What captures their attention isn't just the raw intensity, but its rhythm. Every 4 hours, the central glow swells and then fades in a slow, deliberate cycle. The pulse is unmistakable and steady, almost mechanical in its precision, with energy peaking at the center and radiating outward in organized waves. This isn't random flickering or chaotic outbursts. The data logs fill with precisely measured timestamps, each one marking a rise and fall that repeats with eerie regularity. Alina Morovich and her research group map these intervals against the object's rotation period and orbital parameters, searching desperately for a natural explanation. Nothing lines up correctly. The heat doesn't correspond to surface features rotating in and out of sunlight. It doesn't track with the object's changing distance from the sun. It pulses from somewhere deep inside, completely independent of the changing angle of solar radiation. To the Webb operators studying these patterns, it looks less like a comet's natural outgassing and more like the rhythmic heartbeat of something that was engineered. Radio observatories stretching from California to South Africa turn their arrays toward 3-eyed Atlas, searching for any trace of electromagnetic activity beyond what optical and infrared telescopes can detect. The Allen Telescope Array, under the direction of Dr. Kavita Ralph, begins sifting through hours of wideband radio data. After filtering out background cosmic noise and spillover from satellites, the team isolates something remarkable, a faint narrowband pulse that repeats every 4 hours with unwavering rhythm. Fourier analysis confirms the pattern is real. A stable carrier signal cuts sharply against the background static with a repetition rate far too precise to be random cosmic noise. Over several consecutive nights of observation, the pulse holds steady in its basic rhythm, yet its timing shows subtle variations that correlate perfectly with changes in the solar wind, matching fluctuations tracked by space weather monitoring systems. Independent teams at facilities in Meerkat and Felsberg verify the signal, systematically ruling out local radio interference and any terrestrial sources. The signal's persistence, its subtle environmental responsiveness, and its verification across multiple observatories on different continents forces an uncomfortable question into the open. Is this a natural physical process, or could it be a deliberate transmission from something aware of its environment? By mid-August 2025, the mystery deepens dramatically. Webb's continuous monitoring feed captures a sudden flare. Within less than an hour, 3-eye Atlas brightens by nearly 40%. The TS satellite, still tracking the object from Earth orbit, confirms the dramatic spike. Every telescope trained on the object registers the same surge, and it's not limited to visible light. The thermal output spikes simultaneously. For a brief window of time, the object radiates energy as if something inside has suddenly powered up. Then, just as quickly, the emission stabilizes again, but at a new elevated baseline that remains higher than before. Attention immediately shifts to the object's trajectory. Marco Micheli and the European Space Agency's near-Earth object tracking team run updated orbital models using months of accumulated position data. What they discover is disturbing. The predicted path calculated from all their earlier observations no longer matches reality. Instead of drifting passively along a gravitationally determined course, 3-eyed Atlas has veered. Its trajectory is bending measurably closer to the plane of the solar system. Micheli's group debates possible explanations: outgassing jets pushing the object like tiny rockets, measurement errors in their data, or something far less familiar. The acceleration pattern doesn't fit any documented comet behavior in their extensive databases. For the first time, the compiled data hints at what looks like a deliberate maneuver, with the brightness flare and course change locked together in the observational logs as if they're connected events. The question presses harder now. What kind of object spontaneously changes course in mid-flight through interstellar space? And why would it do so here at the edge of the ecliptic plane? By August 18th, Webb's NIR-SPEC instrument passes the investigation to the spectroscopists. Carrie Lissey's research group at Johns Hopkins Applied Physics Laboratory takes the lead, carefully analyzing the raw spectroscopic data from 3I Vive Atlas. The usual cometary signatures are present in the data: water, ice, carbon dioxide, the standard molecular fingerprints. But layered on top of these familiar markers sits something puzzling. Several absorption lines in the spectrum stubbornly refuse to match anything in known astronomical catalogs. The reflectivity profile hints strongly at metallic alloys, some showing characteristics that echo rare Earth elements found only in advanced manufacturing processes here on Earth. Buried deeper in the data, a handful of spectral features align with theoretical quantum materials, exotic structures described in cutting-edge physics papers but never before observed occurring naturally anywhere in the universe. For the spectroscopy team, the accumulated evidence points unmistakably away from random cosmic chemistry and towards something that appears, at least on paper, to be engineered. As late August arrives, something changes in the scientific community's approach to 3I Atlas. Access to raw telescope feeds begins to tighten. Internal memoranda from NASA and the European Space Agency reference new data handling protocols, citing planetary security concerns. The SETI working group, led by an anonymous coordinator whose identity remains classified, convenes urgent meetings to debate whether humanity should attempt communication. After intense deliberation and a tense vote, they make the decision to transmit. The message is carefully crafted prime numbers as a universal language, elements from the periodic table, fundamental physical constants. 72 hours later, something extraordinary happens. A narrowband reply arrives from the direction of 3I's Atlas, timed to the second. The return pulse shows some distortion from its journey through space, but its pattern precisely matches the transmission window of the original message. Agency officials immediately lock down the data, rerouting all communications to classified channels. Outside the agencies, public speculation surges across social media and news outlets. Inside, the atmosphere shifts noticeably from scientific curiosity to something much closer to institutional caution. At the International Astronomical Union emergency debate held in late August, 4 leading theoretical models are rigorously tested: outgassing jets, radiogenic heating from radioactive decay, complex dust scattering effects, and errors in mass estimation. Each model is found lacking. None can adequately explain the full chain of anomalies documented across multiple independent observation platforms. Now, with September's close flyby rapidly approaching, the countdown intensifies. Every major instrument on Earth and in orbit will be watching, all hoping for the decisive data that finally settles the question of what 3I Atlas truly is. The facts are stark and undeniable. On August 6, 2025, the James Webb Space Telescope recorded 3I's Atlas emitting infrared radiation 3 times brighter than any predictive model suggested possible for its size and distance. Over the following weeks, research teams documented a centralized pulsed heat signature with mechanical regularity, a repeating narrowband radio signal correlated with solar wind variations, and a sudden 40% brightness flare that coincided precisely with a measurable shift in the object's trajectory. These findings have been confirmed through independent observations by TS, Hubble, and European Space Agency orbital tracking systems. Spectroscopic analysis revealed the spectral signatures of rare earth alloys and absorption lines that appear in no current catalog of known materials. Despite multiple independent reviews by top experts, natural explanations including outgassing, radioactive decay, and dust scattering effects have all been systematically ruled out by the International Astronomical Union's expert debate panel. As of late September 2025, 3I Atlas's closest approach to Earth is imminent. Major observatories around the world and in orbit are preparing for the most intensive direct study ever conducted of an interstellar object. What remains absolutely clear is that 3I Atlas challenges every current model we have for understanding interstellar visitors, and its next passage past our planet will represent a decisive moment for planetary science and perhaps for humanity's understanding of our place in the cosmos.